Hello everyone, this is lecture 21, double integrals on general regions. So evaluating double integrals over a rectangular region is a useful place to begin our study of multiple integrals. Problems of practical interest, however, usually involve non-rectangular regions of integrations. So the goal of this lecture is to extend the methods presented in the last lecture so that they apply to more general regions of integrations. So that's the idea of this particular lecture, and hopefully at the end of the lecture, you could be able to recognize when a function of two variables is integrable over general regions. And you could be able to use double integral to calculate the volume of a region between two surfaces or the area of a plane regions, and then simplify the calculations of an iterated integral by changing the order of integrations. So in the last lecture, we encountered double integral. We have run into some integral where you can switch the order of integrations. That is, sometimes you evaluate the function with respect to x first and then with respect to y, or with respect to y first and then with respect to x. So no matter what the order of integrations you do, the answer should be the same. So what is the reason behind changing the order of integrations? The problem is that sometimes you run into some calculations where it makes more sense and is convenient to evaluate the integral of the function with respect to x first and then with respect to y, and vice versa. Therefore, that's what we're going to look into in this particular lecture. Instead of the rectangular regions, now we want to look into regions between two graphs. So when the domain D is a region between two graphs in the xy plane, we can calculate the integral over D as iterative integrals. And we say that D is vertically simple if it is the region between the graphs of two continuous functions, y equal to g1 of x and y equal to g2 of x, as shown in this figure. So this is the case where you have a vertically simple domain, where x is bounded between a and b, and y is bounded between two functions, g1 of x and g2 of x. So here I want to know that this function is g1 of x, and this function is g2 of x. And the domain D is horizontally simple if it is the region between the graphs of two continuous functions, x equal to h1 of y and x is equal to h2 of y. So here is the figure used to present the horizontally simple domain. So y in this case bounded between c and d, and x is bounded between two functions h1 of y and h2 of y. So here is h1 of y, and here is the function h2 of y, and x is bounded between these two functions. Now, in terms of double integral, you can present double integral of the function f of x comma y dA over the domain D as follows. For the case of vertically simple domain, you have the integral from a to b and integral from g1x to g2x of f of xy dy dx. In the case of vertically simple domain, you're going to put in the vertical line, and one end of vertical line touches the bottom functions, and the other end of the vertical line touches the top functions. On the other hand, when you talk about horizontally simple domain, the double integral of the function f of xy dA over horizontally simple domain, the double integral can be written as the integral from c to d, and another integral from h1y to h2y of the function f of xy dx dy. In the case of horizontally simple domain, you're going to put in a horizontal line. One end of the line touches the left functions, and one end of the line touches the right functions. And this is how you're going to evaluate the double integral, where domain is a region between two graphs. Now let's consider the following example. In this example, we want to evaluate the double integral of the function x where y, where D is the shaded region shown in the figure right here. So this is the shaded regions. And the region is bounded by two functions. One is y equal to square root of x, and the other one is with y equal to 1 over x. Now, if you put in a vertical line, one end of vertical line touches the bottom functions, and the other end of the vertical line touches the top functions. So the setup is that I'm going to set up the inner integral first. So the integral of the function x where y dy for y running from 1 over x to square root of x. Now, what about x? So the inner integral is evaluated with respect to y, then the function is evaluated with respect to x. The x value should run from 1 to 3. So 1 and 3, so 3 is obvious in this case because that is the value that's given to us in the graph. The value x equal to 1, sometimes it's a little bit harder to obtain if the value is not directly given to us. So in this case, you can see x equal to 1 is the intersection point between the two functions, y equal to square root of x and y equal to 1 over x. You can actually solve for that as follows. So you're going to set these two functions equal to one another, and you get that square root of x equal to 1 over x. And you're going to square both sides of this equation, and you get x equal to 1 over x squared. And because in this particular case, x is different from 0, so you're going to cross multiply both sides of the equations, and you get x cubed equal to 1. Or when you solve for this, you get x equal to 1. So x equal to 1 is the left endpoint of the interval. Now this is the setup for the double integral that we want to evaluate. With the setup, we're going to evaluate this integral as follows. First, we're going to evaluate the inner integral. And for the inner integral, this is the integral with respect to y, so we're going to treat x as a constant. X is a constant, x squared is also a constant, so we get this is x squared. You pull that out of the integral operations, and you get the integral of 1 over x square root of x of y with respect to y. And then later, you're going to evaluate the outer integral. So the antiderivative of y is 1/2 y squared. So here we're going to get the integral from 1 to 3 of x squared times 1/2 y squared, evaluate at 1 over x and square root of x. So we evaluate the function as square root of x and 1 over x. We're going to get this is the integral from 1 to 3 of x squared times 1/2 times square root of x squared minus 1 over x altogether squared, then dx. And we're going to simplify the integral further as follow. You have 1/2 x squared times x minus x squared dx. Next, I'm going to distribute x squared into the parentheses, and I'm going to get the integral from 1 to 3 of 1/2 times x cubed minus 1/2. And we're going to integrate this function with respect to x. So this is the function in terms of x only, and therefore we're going to get that 1/2 times 1 over 4 times x to the 4th minus 1/2 x, evaluate at 1 and 3. So you get this one is 1 over 8 times 3 to the 4th minus 1 to the 4th minus 1/2 times 3 minus 1. And if we do the calculations correctly, this is going to be equal to 9. This particular problem, you want to evaluate the double integral over this domain. And what we use is we use a vertically simple domain. That is, you're going to put in the vertical line. The bottom end of the vertical line touches the bottom functions, and the top end of the line touches the top functions. Now you may wonder, why don't we use the horizontally simple domain? Now, if that was okay, what you do is you're going to put in a horizontal line. When you put in the horizontal line, you're going to encounter a certain problem as follows. So for this part of the regions, that is fine because it's running from this function to 3. So x is going to run from this function to 3. However, if we slide this horizontal line down a little bit and meet this intersection point, then the limit of integration is going to run from 1 to 3. And then if we move this horizontal line down a little bit, then we have a different limit of integration. That is, the limit of integration is going to run from this function to x equal to 3. So if we choose to do horizontally simple domain, then you have to break it into 3 different regions to consider. And that is actually more work for us to do. Whereas when we just consider vertically simple domain, then you just have one setup for the double integral. So how would you know what to use, when to use vertically simple domain and when to use horizontally simple domain? That is just from experience and from the analysis that you may consider before evaluating the double integral. As you can see, as I analyze the case of horizontally simple domain, you need 3 different double integrals in order to encounter all the limit of integrations that the horizontally simple domain present. Okay, now let's move on to example 2. In this example, you want to find the volume V of the region between the plane z equal to 2x plus 3 and the triangle regions presented in this brown region. So for this region or this domain, the domain is bounded by 2 functions y equal to x and y equal to x over 2. And from the look of this graph, the suggestions is that you may want to consider the horizontally simple domain. So that is, you're going to put in the horizontal line. On the left end is going to touch this left functions, and on the right end of the line is going to touch the right functions. And the setup is going to be, when you evaluate the double integral, you're going to evaluate the function with respect to x first, and then with respect to y. So here's the setup for the volume. So the volume is equal to the double integral of 2x plus 3y dx dy. Now, because you want to evaluate the inner integral with respect to x first, we're going to put in the horizontal line. One end going to touch the function y equal to x, but everything has to be with respect to x. Therefore, you're going to solve for this function y equal to x. That is, x is equal to y. Similarly, from the function y equal to x over 2, we're going to solve for x in terms of y, and that is x equal to 2y. So the limit of integrations of the inner integrals going to run from left to right, or from y to 2y. And then at the same time, if you slide this horizontal line up and down this region, what you could encounter is that the lowest point it can go to is 0, and the highest point it can get to is 2. So therefore, the limit of integration of the integral with respect to y is from 0 to 2. And then at this point, you can evaluate this integral as follows. You get the integral from 0 to 2 of 2 times 1/2 x squared plus 3xy, evaluate at the functions y and 2y. So in this case, you integrate with respect to x, so y is a constant, therefore 3y is also a constant, and therefore the antiderivative of 3y with respect to x is 3xy. And we're going to integrate the function with respect to y. Now we're going to simplify this integrand a little bit before we evaluate the function as 2y and y. So the integral becomes the integral from 0 to 2 of x squared plus 3xy, evaluate at y, 2y, and with respect to y. So here you get the integral from 0 to 2 of 2y squared minus y squared plus 3y times 2y minus y and dy. So if we simplify this, and we're going to get the integral from 0 to 2 of 4y squared minus y squared plus 6y squared minus 3y squared. And if we simplify the integrand further, we're going to get 6y squared. So now the integral becomes the integral from 0 to 2 of 6y squared dy. Take antiderivative of 6y squared, you get 6 times 1/3 y cubed, evaluate at 0 and 2. Well, you have 2 times 2 cubed minus 0 cubed, or 16 for that matter. What if there are some situations where you presented a double integral with the order on which you cannot directly evaluate the integral? So what do I mean by that? Let's consider example 3. So you have the double integral of the form 0 to 4, an integral from x over 2 to 2 of e to the y squared dy dx. So the problem is that there is no basic method for us to evaluate the integral of e to the y squared with respect to y, unless you have a little bit of higher level mathematics. So to resolve the problem, what you do is that you may want to consider switching the order of integrations. So this double integral requires you to evaluate the integral with respect to y first, and then with respect to x. Now we want to switch the order of integration such that we want to evaluate the integral of the function with respect to x first, and then with respect to y, and see what's going to happen. And the procedure for that is, we want to sketch the regions implied by the limits of integrations, and then we write the integral with the order reverse by looking at the region we just determined in the first step. So in this case, in this example, the regions of consideration is that y is between two functions. The function at the bottom is y equal to x over 2, y equal to x over 2, and the top function is y equal to 2, which is the horizontal line. And at the same time, if you move this vertical line left and right, you see that the lower bound of x is at 0, and the upper bound of x is at 4, or at the intersection point between these two functions, y equal to x over 2 and y equal to 2. Right. You can easily find out this particular intersection point right here by letting these two functions, y equal to 2 and y equal to x over 2, equal to one another, or x is equal to 4. We already talked about this order of integration. That is, we cannot evaluate the integral with respect to y first without having higher level mathematics knowledge. So to resolve the problem, we're going to switch the order of integration. Now we want to evaluate the integral of the function with respect to x first, and then with respect to y. So we're going to turn from vertically simple domain to horizontally simple domain. So to do that, we're going to put in the horizontal line here. So on the left end of the line touches the y-axis or x equal to 0. And on the right, the line touches this function, which is, in this case, you have y equal to x over 2, but you want to solve for x in terms of y, so that is x equal to 2y. So from here, we have that x is between 0 and 2y. Now, at the same time, if you slide this horizontal line up and down, you see that the lowest point it can get to is 0, and the highest point it can get to is 2. Therefore, the y value is between 0 and 2. So the double integral that we got from 0 to 4 and then x over 2 to 2 of e to the y squared dy dx can be written as e to the y squared of dx dy, where x is bounded between 0 and 2y, and y is bounded between 0 and 2. Now, evaluating this inner integral is getting a lot easier because you evaluate the function with respect to x, therefore y is a constant, y squared is a constant, and therefore e to the y squared is also a constant. So the antiderivative of this function with respect to x give you x times e to the y squared, evaluate at 0 and 2y. Then later we're going to integrate with respect to y. So you evaluate x at 2y and 0, you're going to have the integral from 0 to 2 of 2y times e to the y squared dy. Now for this integral, we know how to do it. So this is integration by substitution that we learned in calculus 2. Right, we're going to let u equal to y squared and du therefore equal to 2y dy. Now if you solve for dy by itself, you're going to get that 1 over 2y du equal to dy. Because you have just make the variable change, we want to change the limit of integrations as well. So for the limit of integration, I'm going to make a table like this. On one side, I have y. On the other side, I have u. For u is equal to y squared. When y is equal to 0, u is equal to 0. When y is equal to 2, u is equal to 4. Now the integral becomes the integral from 0 to 4 instead of 0 to 2 of 2y e to the u, because y squared is equal to u, and dy is now equivalent to 1 over 2y du. And as you can see, the 2y cancel out, and you're left with the integral from 0 to 4 of e to the u du. And the antiderivative of e to the u is just e to the u, evaluate as 0 and 4. Or you get e to the 4 minus e to the 0, or this is e to the 4 minus 1. And that's how you change the order of integrations. Of course, it depends on the problem. Sometimes it's just straightforward and evaluate the double integral following the order that the problem suggests. But sometimes, for example, in this case, it's hard to directly evaluate this integral with respect to y. So therefore, what we did is we sketched the region implied by the limits of integrations, and then we rewrite the integral with the order reversed by looking at the region we just determined. Okay, now let's move on to the next example. In the next few examples, we would like to sketch the domain of integration and express the integral in the opposite order. So in this case, we're not going to do any evaluations. We're just going to sketch the domain implied by the limits of integrations, and then rewrite the integral with the order reverse by looking at the region that we just determined. Okay, so the regions that we need to draw here is that x is between 0 and 4, and y is between x and 4. So here from the limit of integrations, we have that y is between x and 4, and x is between 0 and 4. So we're going to plot this on the xy plane. So this is x, this is the origin, and this is y. You have the lower bound here is y equal to x, and the lower bound is y equal to 4. So y equal to x is the line going through the origins like this, and y equal to 4 is the horizontal line. So here is y equal to x, here is y equal to 4, so this one is 4, and at the same time, x is bounded between 0 and 4. So here you want to consider, originally, you want to consider the vertically simple domain. So that is, you want to put in a vertical line. Now let's double check if this is the vertically simple domain. That is, the lower end touches the function y equal to x, and the upper end touches the line y equal to 4. So this check out. And if you move this vertical line up and down the regions, you can see that the lower bound of this would be 0, and the upper bound should be x equal to 4. Right? And this can also be determined by the intersection point between the two functions. That is, if you let y equal to x and y equal to 4 equal to one another, you see that x is equal to 4. Now, in order to switch the order of integrations from, in this case, a vertical line to horizontal line, or from vertically simple domain to horizontally simple domain, what you're going to do is we're going to put in a horizontal line. So for this horizontal line, the line touches the left end at the y-axis, or x equal to 0. So x is bounded between 0, and on the right hand side, or the right end, the horizontal line touches the function, this function, x equal to y. So this is x equal to 1. Now at the same time, if you move this horizontal line up and down the regions, you can see at the lowest point it can get to is 0, and the highest point it can get to is 4. So here you have y is bounded between 0 and 4. Therefore, for our double integral from 0 to 4, and integral from x to 4 of the function f of xy dy dx, we can rewrite this, and we get the double integral of the function f of xy of dx dy, where x running from 0 to y, and y running from 0 to 4. Now we're going to move on to the next example. In this example, we're going to follow the same step as we did in problem A. So here we're going to sketch out the domain of integrations based on the limit of integrations given to us. So here we analyze and we see that the double integral is evaluated with respect to x first and then with respect to y. So x is running between 2 and the square root of y. At the same time, y is bounded between 4 and 9. So we're going to plot these regions on the xy plane. So here is the coordinate system, x, origins, and y. So x is bounded between 2 and square root of y. So x equal to square root of y indicates that this is y equal to x squared, but we're going to use just one part of the parabola. Technically, the right part of parabola. So that is, this is the parabola. X equal to square root of y, or y is equal to x squared. Now, at the same time, x is bounded below by 2, so you need to put in a vertical line of x equal to 2. So this is 2. And between these two functions, the intersection point is y equal to 4. So this is x equal to 2. And at the same time, y is bounded between y equal to 9 and y equal to 4. The regions of considerations is this regions. By the suggestions of the problem, is the horizontally simple domain. So that is, if you want, you can put in the horizontal line, and the left end of the line touches the vertical line x equal to 2, and on the right end it touches x equal to square root of y. And then if you move this horizontal line up and down the regions, you have that the lowest point it can get to is 4, and the highest point it can get to is 9. Now, to switch the order of integrations, that is, you want to change the integral with respect to x first and then with respect to y, to integration with respect to y first and then with respect to x. Here, I'm going to put in a vertical line. The lower end of the vertical line touches the curve x equal to square root of y, or in this case, it has to be y equal to x squared. So here, you want to write y is bounded below by x squared, and bounded above by this line, y equal to 9. And at the same time, if you move this vertical line to left and right of the regions, we're going to see the lowest point that it can get to is x equal to 2, and the highest point it can get to is this intersection point, which is 3 in this case. And we can get that by solving the intersection between the two functions, y equal to 9 and y equal to x squared. And you're going to get that y equal to 3 is one of the options. If you consider y equal to negative 3, it's not part of the regions of considerations. So x in this case is going to be between 2 and 3. double integral of the function f of xy dx dy for x running from 2 to square root of y and y running from 4 to 9. And we're going to change the order of integrations of f of xy dy dx for y running from x squared to 9 and x running from 2 to 3. Now moving on to problem C. In this problem, the double integral of the function is evaluated with respect to x first and then with respect to y. So therefore, we analyze that x is bounded between square root of y and 3, while y is bounded between 4 and 9. So we're going to plot these regions on the xy plane as follows. This is x, this is the origin, this is y. So the function x equal to square root of y, or y is equal to x squared, is the parabola. And at the same time, x is bounded above by 3. So x equal to 3 in this case. And you have y is bounded between 4 and 9. So here is 4. So y equal to 4. And here is y equal to 9. And this is the regions of considerations. So from the given integral, the region is first considered using the horizontally simple domain. That is, if you put in the horizontal line, you see that the left end touches the function x equal to square root of y, or y equal to x squared for that matter. The right end point is bounded by the vertical line x equal to 3. And then if you move this horizontal line up and down the regions, the lowest point can get to is y equal to 4, and the highest point can get to is y equal to 9. Now, if you want to switch the order of integrations, we're going to put in a vertical line. The lower end of the line touches the function y equal to 4. So you have y is bounded below by 4 and bounded above by this functions. You have x equal to square root of y. And when you solve for this, you get y is equal to x squared. So here y is bounded above by x squared. And then if you move this vertical line left and right of the regions, the lowest point it can get to is this particular point right here, which is the intersection between the function y equal to x squared and y equal to 4. And if you set the two functions equal to one another, you're going to get that x squared equal to 4. Usually you're going to get two solutions, that is plus or minus 2. But in this particular context, you're just going to choose the positive value. In this case, x is equal to 2. So at the same time of y bounded between 4 and x squared, x is bounded between 2 and 3. So the double integral of the functions f of xy dx dy for x going from square root of y to 3 and y going from 4 to 9 can be written as the double integral of the function f of xy dy dx for y running from 4 to x squared and x running from 2 to 3. Now we're going to consider one last example in this category. That is, you want to change the order of the double integral from integrating the function with respect to y and then with respect to x to the double integral where you want to evaluate the function with respect to x first and then with respect to y. We're going to sketch the regions of consideration from the limit of integrations. So here's the xy coordinate system. From the given problem, we see that y is bounded between two functions, e to the x and e, and x is bounded between 0 and 1. So for the function y equal to e to the x, it has the form like this. And this is y equal to e. So this is e, this is the function y equal to e to the x. And this intersection between the two functions is 1. So from these suggestions from the problem, you see you first consider the domain to be vertically simple domain. That is, you're going to put in a vertical line, and the lower end of the line touches the function e to the x, and the upper end touches the function y equal to e. If you move this vertical line left and right of the regions, we're going to see that the lowest point it can get to is x equal to 0, and the highest point it can get to is x equal to 1. Now to switch the order of integrations, I'm going to put in the horizontal line. The left end of the line touches the y-axis or x equal to 0. So in this case, you have x is bounded below by 0 and bounded above by this curve. And this curve has to be written as the function of y. That is, you want to solve for x in terms of y. To do that, we're going to take ln on both sides of these equations. And we're going to obtain ln of y equal to x. So x is bounded below by 0 and bounded above by ln of y. And if you move this horizontal line up and down the regions, the highest point it can get to is E, and the lowest point it can get to is this point right here, which is the intersection between the curve y equal to e to the x, or x equal to ln of y with the vertical axis, or in this case, y is bounded below by 1. So the double integral of the function f of xy dy dx, bounded for y running from e to the x to e, and x going from 0 to 1. And if you want to switch the order of integrations from to dx dy, you're going to get x bounded between 0 and ln of y, and y is bounded between 1 and e. And that's how you change the order of integrations, by first sketch the regions implied by the limits of integrations, and then rewrite the integral with the order reversed by looking at the region we just determined. Now we're going to move on to the last example of this lecture. In this example, we want to evaluate the integral by changing the order of integrations. Okay, so not only we need to change the order of integration for this problem, we need to evaluate the integral as well. Now let's analyze this double integral for a moment here. If you want to evaluate this integral, this inner integral with respect to y, you see that this is not an easy integral or direct integral to find the answer to. So therefore, it's good to switch the order of integrations from dy dx to dx dy. And before doing that, we need to sketch the regions of considerations based on the limit of integrations. So from here, we see that y is bounded between two functions q root of x and y equal to 2. At the same time, x is bounded between 0 and 8. So we're going to plot this on the xy plane. This is x, this is the origins, this is y. So y equal to q root of x, so the function will look more or less like this. Y equal to 2, so the curve is y equal to q root of x, and the horizontal line is y equal to 2. And because we evaluate the double integral with respect to y first, so what you consider, so the domain of consideration has to be the vertically simple domain. So you can put in the vertical line here. The lower end touches the functions y equal to q root of x, and the upper end touches the function y equal to 2. And if you move this vertical line left and right of the regions of considerations, the lowest point it can get to is 0, and the highest point it can get to this intersection point. In this case, going to be equal to 8. Now to change the order of integrations, we're going to put in the horizontal line. The left end of the line touches the y-axis, that is, x is bounded between 0, and the upper bound is going to be this function. You have the function of y equal to q root of x. Now we need to rewrite this function so we obtain x in terms of y, that is x equal to y cubed. So in this case, x is bounded between 0 and y cubed. And if we move the horizontal line up and down the regions, we can see that the lowest point it can get to is 0. And the highest point it can get to is 2. So instead of the double integral written in this form, we're going to get the double integral from 0 to 8, the integral from q root of x to 1 over y to the 4 plus 1 dy dx. This is equivalent to the double integral from 0 to y cubed and 0 to 2 of 1 over y to the 4 plus 1 dx dy. And because we evaluate the inner integral with respect to x first, y is treated as a constant. So this fraction is a constant. So the antiderivative of that is going to be the integral from 0 to 2 of 1 over y to the 4 plus 1 times x, evaluate at 0 and y cubed, dy, or you get the integral from 0 to 2 of y cubed over y to the 4 plus 1 dy. Now this is a lot easier to evaluate. To integrate this function, we're going to use integration by substitutions. That is, you let u equal to y to the 4 plus 1, or du is equal to 4y cubed dy, and then you solve for dy, you get 1 over 4 y cubed du. Because you make the change in variable, you want to make the change in limit of integrations as well. So the table consists of two columns. The first column is y, the second column is u. When y is equal to 0, u is equal to 0 to the 4 plus 1 equal to 0. When y equal to 2, you have 2 to the 4 plus 1, or this is going to be equal to 17. Now the integral becomes the integral from, instead from 0 to 2, now you have from 1 to 17 of y cubed divided by the denominator is y to the 4 plus 1. In this case, gets substituted for u, and dy can be written as 1 over 4y cubed du. Now you're going to make some simplifications here. Y to the third power cancel out. 1 to the fourth is a constant multiple, so you can bring that out of the integral operations. You're left with the integral from 1 to 17 of 1 over u du. Or this is 1 over 4 times ln of absolute value of u, evaluate at 1 and 17. Or you get 1 over 4 times ln of absolute value of 17 minus ln of absolute value of 1. ln of 1 is equal to 0, so you're left with the answer ln of 17 over 4. We can actually drop the absolute value because 17 is a positive number. So that's it for me. Please let me know if you have any questions. Thank you.